So lecture number 51, I'll continue with the bridge rectifier, which I did in the last lecture with you. The circuit diagram is this, and this is the working. If I apply a input voltage Vi at the secondary of this, of course, which is obtained after being stepped down by this transformer, Vm sin omega t, the corresponding output which I obtain is equal to Im sin omega t for between 0 to pi or pi to 2 pi or 2 pi to 3 pi. We get this as Im sin omega t, and this Im is equal to Vm upon 2 Rf plus RL. That is very important to understand here. Now, just a very quick recall. If I apply a voltage, if this is the input voltage Vi, I am repeating this. If for a bridge rectifier, it is in continuation with a bridge rectifier. Analysis of a bridge rectifier. I'll write here, it is bridge rectifier. I am dealing with bridge rectifier. So if this is the input voltage Vi, if this is the input voltage Vi, and if the instantaneous value of this Vi is equal to, this is omega t, of course this is 0, pi, 2 pi, 3 pi and so on. If the instantaneous value of this is Vm sin omega t, that is, if this is Vm, this is Vn, then the corresponding output which I obtain is a DC wave, a pulsating DC. Again, I drop down these points here. These are the points drop down, same as 0, pi, 2 pi, 3 pi, 4 pi and so on. And the kind of signal which I obtain here is a pulsating DC, but we obtained, how the working is that we have already discussed. It is something like this, a full wave DC, which has swings only on the one side, not on both sides. So it is a pulsating DC. Now what I said, and the instantaneous value of this is Im sin omega t, Im sin omega t, where this is Im. This is the output voltage I. Output current, the output across this load which I obtain, and how the working I have already discussed with you. Now see, so what we said, that if the input voltage, if this input voltage Vi, the applied input voltage, if the applied input voltage Vi is equal to Vm sin omega t, then the corresponding output current, this is the output current IL, I say, or simply I say that this is the output current I, or in many books it is IO, one is the same thing. IL is equal to Im sin omega t. Im sin omega t for omega t between 0 to pi or between pi to 2 pi. See, this is the case for omega t between, I am taking only one period, 0 to pi. If you look at this, the period of this signal, of this overall this signal is pi, because it is repeating after pi. Same, either you say pi minus 0, same signal, 2 pi minus pi, which is pi, same signal, 3 pi minus 2 pi, same signal, it is equal to this much. And at the same time, the value of Im maximum, this maximum is equal to, this Im is equal to Vm upon twice of Rf, where Rf is the forward resistance offered by each diode. I assume that all the diodes are identical and every diode is offering a resistance, equal resistance Rf. So this Im is equal to Vm upon 2 Rf plus RL. On the other hand, in case of either I talk about center type full wave rectifier or half wave rectifier, this Im was equal to Vm upon Rf plus Rl. That is the main difference that lies mathematically in bridge rectifier and all other rectifiers. Now let's see the analysis of this. Again, I'll find the value of DC current or the average current. Let's find out the output current, the DC or the average current. Average current, of course output current I am talking about. That is, what is the DC value or the average value of this, IDC or I average. Suppose I say that this is the average value or the DC value of this. I name this as, suppose this is IDC or I average. So IDC or average value of this. I have told you how to find the average value. That is, you integrate over one period and divide by the time period, you'll get the average value of this. So you integrate this, that is I d theta. I assume this omega t by theta. I'll replace this omega t by theta. I d theta, one period when omega t or theta. Theta is what? I replace, I say that let omega t is equal to theta. I assume this. So I d theta over one period is 0 to pi, and integrate over one period, divide by the time period, that is 1 upon pi. So it is 1 upon pi, 0 to pi, I d theta. Now value of I for 0 to pi is Im sine omega t. So you can say that this is equal to IDC or I average 1 upon pi integral 0 to pi, and the value of I is Im sine theta. Im sine theta d theta. For 0 to pi, this value is Im sine theta. It is same, Im sine theta. Whether you talk about this period or you talk about this one or this one, it is Im sine theta. And since we have done this derivation already in case of center type full wave rectifier, because it is same signal and same output here, the only difference lies is this value of Im. So I can say this implies that value of IDC or I average is equal to twice Im by pi. We have discussed this already. Twice Im by pi, and similarly you can say, similarly I am writing, I am not deriving it. Similarly, VDC is equal to twice Vm by pi. That is the DC value of the output voltage. Of course, output voltage will also have the same nature, and the DC value of this VDC is equal to twice Vm by pi. So this is the first article, that is, what is the DC or the average value. First performance parameter. Second, what is the RMS value? RMS current. I am finding current, then I will find the voltage also. RMS current. I name this as IRMS. This is the next performance parameter. IRMS. Now, how to find the RMS value? That I have already discussed. Mathematically, you square the function, take the mean or the average, and find the under root of this. So first of all, RMS, you square the function. S means square. So I square the function, that is I square. Then take the mean. Again mean, how to find the mean? Area under one period, that is integration 0 to pi, divide by the pi time period d theta. Square the function, take the mean, and find the under root of this. You find the under root of this will give you the RMS value of the output current. I am finding the RMS value of this signal, not of this signal. So it is quite simple. We have done this many times. It is under root of 1 upon pi integral 0 to pi. It will be 0 to pi. For 0 to pi, I is equal to Im sin theta. For 0 to pi, I is equal to Im sin theta. So I square will be Im square sin square theta. Im square sine square theta d theta. And we have done this in the previous case also, so I am not doing it. You take this I am out of this integral sign as well as from this under root sine square theta 1 minus cos 2 theta upon 2 and put the limits. So directly you will get, I am not doing the intermediate calculations here. So you will have IRMS from here. Value of IRMS will be Im upon root 2. Same kind of mathematical derivation as we did in case of the center tap full wave rectifier, because it is the same wave, same analysis. The only difference lies in the value of Im, that is Vm upon twice Rf plus Rl. And of course, this is RMS value of the output current. And similarly, I can say that VRMS, RMS value of the output voltage, will be Vm upon root 2. So we'll use these as a formula. These are the performance parameters, some of the performance parameters of this bridge rectifier. Let's take one more parameter, and that is the efficiency. Let's take the efficiency. Efficiency of course, bridge rectifier. We are dealing with bridge rectifier, which is a full wave rectifier. Efficiency of a bridge rectifier. And it is represented by neta. Now, I told you that the efficiency, as far as the definition of efficiency is concerned, that we have already discussed, it is the DC output delivered to the load, the output DC power delivered to the load to the input AC power. DC power delivered to the load to the input AC power. This is the efficiency of any rectifier. In general, we have defined this, that the efficiency is equal to P DC upon P AC. Now, let's see that how we find this P DC and P AC in case of a bridge rectifier. Now, we have already derived PDC. If I say what is PDC, what is the DC value of the output? PDC means the DC power across this load. I am interested in the power across this load, and the current flowing here is of course IDC. This is the current that we obtain across this after the application of the circuit here. So it is very clear that the value of PDC from here, the value of PDC is equal to IDC square into RL. PDC is equal to, this is IDC square into RL. P is I square into R. So it is IDC square into RL. I'll write it right now, this much only. And the value of PAC, the value of PAC, that is the AC input power. This is the AC input power. Remember that this is output and this is input. PAC, whenever AC is there, I'll have to use RMS value. So I use the RMS square into RF plus RL. Into RF plus RL. This is point that I have discussed with you many times, that whenever you take the value, that is the RMS value for PAC. Just hold on for a second. So now this is PAC is I RMS square into RF plus RL. So now let's find out the value of neta. Neta is equal to IDC square into RL. PDC, I can say it is equal to IDC square into RL upon PAC is IRMS square into RF plus RL. But the point that we have to discuss here, in case of a bridge rectifier, is that IDC. If you see what is the value of IDC, IDC we have just derived, it is equal to twice Im by pi. and IRMS square, it is not only this much, it will be 2RF plus RL. That is the main difference that lies. PAC will be IRMS square into, in spite of RF plus RL, which we discussed in all the rectifiers, but here it will be twice of RF plus RF, so it will be IRMS square into twice RF plus RL. I hope that this point is clear to you. This is the only difference which lies. So now it is IDC square into RL upon IRMS square into this much. Value of IDC we have just derived. IDC is equal to twice IM by pi. We've just derived that this is equal to twice IM by pi. So I write this as twice IM by pi whole square into RL upon IRMS is Im upon root 2. We have just derived, it is equal to Im upon root 2. So this is equal to Im upon root 2 whole square into 2 RF plus RL, twice RF plus RL. Now if you observe this, the neta, this Im will cancel, and this will be 2 to the 4, 4 to the 8, 8 upon pi square. It will be 8 upon pi square. This value is equal to 8 upon pi square into RL upon twice RL plus RF. RL upon twice RF plus RL. Im will cancel. 2 to the 4, 4 to the 8. This 2 will be in the numerator, pi square. So it is 8 upon pi square. So this is the value of efficiency, 8 upon pi square into RL upon twice RF plus RL. Now suppose I am interested in what is the value of neta maximum. When will we have the maximum efficiency of this? So for neta is equal to neta maximum, for maximum value of neta, for maximum value of neta, which I say that, suppose it is, I name this as neta maximum. Now for maximum value of neta means for maximum efficiency, the efficiency will be maximum in the case when we assume that this diode is an ideal one. These diodes are ideal, means these are offering zero resistance, means this value of RF is equal to 0. So maximum efficiencies will occur when RF is tending to 0. So it is very clear that for this, if you find this, that is from this equation, suppose I say equation A, this is equation A here. In this equation, if I substitute this RF is equal to 0, this RL and RL will cancel. So I can say that the value of neta maximum will be 8 upon pi square. Or if I say what is in percentage, neta maximum in percentage, it will be equal to 8 upon pi square into 100. And if you find this implies that the value of neta maximum in percentage, if you find it, this comes out to be approximately equal to 81.2%. This is the maximum efficiency of a bridge rectifier, which is same as that of maximum. I am talking about the maximum one, same as that of a center tap full wave rectifier. On the other hand, in case of half wave rectifier, if you remember the maximum efficiency of half wave rectifier, it was approximately 40%, 40.5% or 40.5% approximately, and here it is approximately 80%. So the efficiency of bridge rectifier is double the efficiency of a full wave rectifier. I can say either center tap or bridge rectifier, it is double the efficiency of a half wave rectifier, and that is the advantage of a full wave rectifier as compared to a half wave rectifier. So I'll stop it here. Thanks for the time being.